Okay. Now, what we have to do is we have to find capital R, capital theta and capital phi such that their product will satisfy this equation. So, to determine capital R, capital theta and capital phi, what we will do is we will use this product and put it in place of psi here as well as on the right hand side. Now, because I need space, I am going to rub off this equation, but to remind you, let me keep it here. This is our Schrodinger equation, and we are trying to solve it using the method of separation of variables, where we assume that psi may be written as a product of three functions, capital R, capital theta and capital phi, capital R depending only upon small r, capital theta depending only upon small phi, small theta, and capital phi depending only upon small phi. So, what we do is we take this and put it into the full Schrodinger equation. So, wherever psi occurs, we are going to put that. So, let me rub off this psi and put capital R, capital theta and capital phi, and do the same thing here on this side. And now, if we looked at this operator, the operator involves partial differentiation with respect to r, theta and phi. But in here, this operator contains only partial differentiation with respect to r, and in that partial differentiation, variables theta and phi are kept constant. So, therefore, capital theta and capital phi will be unaffected by this operator. So, therefore, if I took this function inside, what will happen is that this operator will affect only capital R, it will not affect capital theta or capital phi, and therefore, let me write what the result is. So, this operator affects capital R, but it does not affect the two things. So, the two other things actually can be taken and written here. And similarly, this operator will affect only capital theta. So, we can do a similar thing with that operator. What would be the result? The operator affects only capital theta of theta, and similarly the last operator affects only capital phi. So, let me write that. And capital R and capital theta are unaffected, so I can write them here. And let me now complete this bracket, then write this term, which is minus e square divided by 4 pi epsilon 0 r. Okay. Yeah, well, I have forgotten to put capital R, capital theta, capital phi of phi, and that is actually equal to E into capital R of r, capital theta of theta, capital phi of phi. Now, the next thing that we will do is we will divide throughout by the wave function itself, and the reason for doing that will become clear as I proceed. If I divide it throughout by this function, I divide throughout by this function, then obviously from the left hand side this is going to go, and here from this term also the term is going to disappear, while in these terms, so what is going to happen, in here you are going to divide by capital R of R, capital theta of theta and capital phi of phi. Obviously as far as this term is concerned, there is a capital theta and a capital phi in the numerator, so these two things and those two things will get cancelled and you will be left with capital R of R in the denominator. So without writing the equation once more, this is already a long equation, so without writing the equation once more, I will just rub off this and write 1 by capital R of R. And the same kind of thing is going to happen here in this. You have capital R and capital phi in the numerator, they are going to get cancelled and you will be left with a 1 by capital theta of theta. And what about this one? Well, capital R and capital theta will go, you will have 1 by capital phi of phi. Now capital R into capital theta into phi, I have already told you this will disappear and this also will disappear. And because this E, which is the total energy, it is sitting so far away, what I will do is I will bring it closer and write the equation in this fashion. Okay. So this bracket also let me just close, I will put it here, which is the correct place to put it. And so this is the equation that we will use now. So let me rewrite this equation. That is the result, right. You can check that I have not made any mistake. But then when you look at the equation, you see I have written one part in a different color. What is the speciality of that part? If you look at it carefully, you would realize that that is the only part that depends upon small phi. You do not find a dependence upon small phi anywhere in the equation, that is why I used a different color. So you have the left hand side of the equation, there are r, theta and phi, but this part alone depends only upon phi, while everything else depends upon r and theta. So if you have this kind of equation, what can you do? You can rearrange this, you see first you will take this term to the other side, then you will multiply by the inverse of this, after which you will take these terms also to the other side. Eventually you can rearrange in such a fashion that only this term is left on the left hand side. And what about the right hand side? Right hand side will be some function of r and theta, and whenever you have such an equation, we know that, see, on the left hand side you have a function of phi, and on the right hand side you have some function of r and theta, and if such a thing is to be satisfied, both of them must be equal to a constant. So therefore this function of phi definitely must be equal to a constant, and I am going to call that constant, right. So I am led to the conclusion that this must be equal to a constant, which I will denote as minus m square. You can have any notation for it, but the standard notation is to use minus m square. You should not confuse this with the mass of the electron. It is not the mass of the electron. Eventually it will turn out to be the magnetic quantum number, and as you know, magnetic quantum number is usually denoted by the symbol m. So I am not going to change the notation. So what is the conclusion? Conclusion is this object has to be equal to minus m square, which actually tells me that 1 by capital phi of phi, well, it is not really necessary to use partial derivative notation here, because phi, capital Phi depends only upon small phi. So I could have written this as d square capital Phi by d phi square is equal to minus m square as the equation that I get. Or if you multiply throughout by capital Phi, what happens is you will get d square capital Phi by d phi square is equal to minus m square capital Phi of phi. This is a fairly simple differential equation and you can solve it, right, not difficult to solve at all. So therefore we have successfully found what phi should be. I mean, we will solve it later, but we have found an equation that capital Phi satisfies, right. And so then what will I do next? Well, this is equal to minus m square, so instead of this part I can actually say I will put minus m square there, because it has to be equal to a constant. So let us put minus m square, that term, instead of that term you just write minus m square, and what happens, you have this equation, correct. And I am going to write this equation once more, but because I will need this equation later, maybe I will move it to this side. So I will write this equation once more, minus h cross square by 2 mu 1 by capital R of r square dou by dou r square dou r by dou r plus 1 by r square. You can see there is a 1 by r square here, another 1 by r square there. So let me write it as a common factor. What is inside this bracket? It's actually 1 by sin theta dou by dou theta sin theta dou capital theta by dou theta of theta minus m square divided by sin square theta, right, and of course you have 1 by r square, I have taken that out, and then plus, well actually not plus but minus E square divided by 4 pi epsilon 0 r is equal to E. Right. Now, if you look at this equation, what do you find? The portion that I have written with the yellow color depends only upon theta, while everything else is either constant or dependent on r. So, what can you do? You can rearrange this. You can rearrange it in such a fashion that only this term is left on the left hand side, only this term remains on the left hand side, and then you will say that a function of theta is equal to some function of r. Theta and r are both independent variables. So, in the spirit of method of separation of variables, you will have to say that both of them are equal to a constant. So, that specifically implies that this must be equal to a constant. Let me write that equation. There is a minor mistake in what I have written. I have forgotten to write this capital theta. That should have come here. So, let me write that also. Capital theta of theta will be occurring here. So, 1 by capital theta of theta sin theta dou by dou theta sin theta dou by dou theta operating upon capital theta of theta minus m square by sin square theta must be equal to a constant. That is what I am saying. And what I will do is I will use the symbol minus beta for this constant. So, therefore, if I like, I can rearrange this, I can rearrange this and get an equation for differential equation for capital theta. Okay. So, how will I rearrange it? I will first take beta to this side and then multiply throughout by capital theta. So, let me write that result. 1 by sin theta dou by dou theta sin theta dou capital theta by dou theta plus beta minus m square by sin square theta into capital theta is equal to 0. Okay, that is the equation for capital theta, and it is an ordinary differential equation. In fact, it is not really necessary to put partial derivative notation, because the function on which these things operate are just functions of the variable theta alone. So, you could have just put d there. And not only that, this whole thing is equal to a constant. So, therefore, I can put, instead of that whole thing, I can put minus beta. And if you put minus beta, what happens? You get an equation for, look at what has happened. This is just an equation for capital R. So, what is that equation? I will have to write it somewhere. That equation I will write in the middle. Well, I will multiply throughout by capital R, so that it appears as a nice differential equation. So, that is how it is. Fine. So, we have arrived at 3 separate ordinary differential equations, and I would like to solve these 3 equations, and of course, any solution that I find will have to be acceptable. I mean, that is a condition that we have to impose. So, we start with the first equation because it is the simplest. So, the first equation says that d square capital phi by d phi square is equal to minus m square capital phi of phi. Now, I would also like to remind you that any function that you get has to be normalized. Okay. What does that mean? That actually means if you took psi star psi and integrated over the full volume element, sorry, integrated over the full space, you multiply it by the volume element d2 and integrate over the entire space, the answer must be equal to 1. And in Cartesian coordinates, actually this is a reasonably simple expression. You will have to take dx into dy into dz, and the answer has to be 1. But we have decided to throw away Cartesian coordinates and express everything in terms of r theta phi. So, what does that mean? It means that the psi that I find, which will be a function of r theta phi, I will have to multiply it by its own complex conjugate r theta phi. Then I will have to multiply it by the volume element d2. Okay. So, that means this volume element d2 has to be expressed in terms of r theta phi, right. Here the expression for volume element in terms of Cartesian coordinates is simple, it is just dx into dy into dz. The expression for the volume element in terms of spherical polar coordinates is slightly more complex. We will not discuss this, but I will just say that in polar coordinates what happens is that the volume element actually becomes r square sin theta dr into d theta into d phi. That is what happens. This is just your d2. Okay. And you have to integrate over the entire space. How will you do the integrations over the entire space? It will be a triple integral because you have 3 variables. Now, the variable r will vary, minimum possible value if you remember is 0, it will go to infinity, right. Just to remind you that this is integration over r, what I will do is I will remove this dr from there and put it here. And then I have to integrate over theta. Theta, I told you, to cover the entire space you need to allow it to range from 0 to pi. So, therefore, you will have 0 to pi d theta. So, I can remove that d theta from there, and then finally, you have d phi. Let me put the d phi here, that is the third integration, and that will have to range from 0 to 2 pi. So, that is why I will have to do the integral, right. And now, if I looked at my wave function, what has happened? The wave function has been assumed to be a product, correct. So, what is the nature of the product? It is going to be capital R, capital theta, capital phi, everything starred, multiplied by capital R of small r, capital theta of small theta and capital phi of small phi, correct. So, if you substitute this product here, you would realize that the integrals that you have to perform, they become three separate integrals. That is should be clear to you. And what are those integrals? Let me just write those integrals. One of them will be integral 0 to infinity dr. I just collect together the terms that depend upon r, dr r square capital R star capital R. Then the next integral will be integral 0 to pi d theta sin theta capital theta of theta star capital theta of theta, and integral 0 to 2 pi capital phi star phi capital phi of phi d phi, and this must be equal to unity, correct. This is the normalization condition. And so, what we will do is, you see, I am going to solve this equation. Similarly, there are equations for capital R and capital theta which also have to be solved. But after having found those solutions, what I will do is, I will impose conditions on them which will say that this integral must be equal to 1. And I shall impose condition on theta saying that this must be equal to 1, and this other integral that also must be equal to 1. So that once I have found functions in this fashion, I am assured that the wave function, the total wave function is normalized, because if each one of them is equal to 1, then the product has to be equal to 1. Okay. So, that is what I will be imposing. So, therefore, what happens is that this differential equation I am going to solve and adjust it in such a fashion that this condition, which is the normalization condition, is satisfied as far as that part is concerned. Similarly, when I have capital theta, I will have to normalize that, and similarly capital R also has to be normalized. So, what is the solution of this equation is the next question. Answer is very simple. Any constant a into e to the power of I m phi satisfies that differential equation. But then the question arises whether this is an acceptable solution. See, suppose I am thinking of having my head, as I said, in the x z plane, but that is not very precise actually. Suppose I am standing somewhere here, this is me and here is my head. Okay, this is the positive x direction and that is the z axis. So, my head is in the plane formed by the positive x axis and the z axis. So, if that is where I was standing, then you know that the value of phi is equal to 0. But you can also say that in the same plane the value of phi can be thought of as 360, which is 2 pi radians. So, phi equal to 0 and phi equal to 2 pi are completely equivalent, right. For any point you can say phi is equal to 0, or equivalently well you can say phi is equal to 2 pi. So, therefore, let me say I am going to evaluate the value of this function in that plane, anywhere in that plane. What will I do? Well, I may say, okay, if the value of small phi is 0, so what will happen? I will get the answer to be a e to the power of 0, which obviously is 1. But one of you may say, no, I do not want that value of the angle phi, but what I will do is I will put 2 pi, right. So, if you put 2 pi, what will happen? The answer that you are going to get will be a e to the power of I m 2 pi. And if the function is to be single valued, these two answers have to be the same, you cannot have a different answer. And then what is the condition? The condition would be that e to the power of I m 2 pi must be equal to 1. So, therefore, you realize that this m is not arbitrary, m cannot have any value. I mean, we introduced it as a constant, we did not know what its value was, but now we realize that this m has to be such that e to the power of I m 2 pi must be 1. So, what are the different possible values of m which will satisfy this condition? The first possibility is to have m equal to 0. The next possibility is m is equal to plus 1, because if you put m equal to plus 1, you will have e to the power of I 2 pi, but there is a theorem of De Moivre's which tells me that e to the power of I theta is equal to cos theta plus I sin theta. There is a theorem due to De Moivre which says that. So, therefore, if you had e to the power of I 2 pi, then it will be cos 2 pi plus I sin 2 pi. And sin 2 pi is 0, cos 2 pi is 1. So, even when m is equal to plus 1, you find that the condition is satisfied, but you can easily verify that m may be minus 1, not only plus or minus 1, but m can also have the values plus or minus 2, plus or minus 3, etc. So, therefore, in order to satisfy this condition, the value of m should be 0, I mean could be 0, plus or minus 1, plus or minus 2, etc. Any positive or negative integer or 0. Okay. And then the next question will be, what should be the value of capital A? Well, this is your wave function. We know that I have to choose capital A in such a fashion that the wave function multiplied by its own complex conjugate integrated from 0 to 2 pi must be equal to 1. This is what I have to do. So, if you use this condition for this particular function, what is going to happen is this will be a e to the power of I m phi, complex conjugate of phi will be a e to the power of minus I m phi, and you have to multiply by d phi and integrate from 0 to 2 pi. And it is obvious that in this expression, this e to the power of plus I m phi will be exactly cancelled by e to the power of minus I m phi. So, these two will cancel each other, and you will be left with integral 0 to 2 pi a square d phi is equal to 1. Remembering that a square is just a constant, actually referred to as the normalization constant. This integral can be easily done. You will find that a square into 2 pi is equal to 1, which implies that a suitable value for the normalization constant is a equal to 1 by square root of 2 pi. As a result of which the normalized wave function, this capital phi, will become capital phi of phi is equal to 1 by square root of 2 pi e to the power of I m phi. So, therefore, we have found the complete, I mean the all the possible solutions of this equation. The solutions are of the form phi is equal to 1 by square root of 2 pi, correct? Because I find that a square into 2 pi is equal to 1, that means a is equal to 1 by square root of 2 pi. So, 1 by square root of 2 pi into e to the power of I m phi is the solution. Now, this m can have the values 0 plus or minus 1 plus or minus 2 etc. Specifically, if you put m equal to 0, what is the answer that you get? You get just a constant. Okay. Well, you see that this solution, this function actually depends upon a number m, right, which we will refer to as a quantum number. Specifically, it is referred to as the magnetic quantum number, and to denote its dependence, we will put a subscript phi m. So, if I am looking at phi 0 of small phi, it is going to be 1 by square root of 2 pi. What will happen to this part? If m is 0, it is just a constant, and then you can think of phi either plus 1 or minus 1. What will you find? You will find that the answer is 1 by square root of 2 pi e to the power of either plus I phi or 1 by square root of 2 pi e to the power of minus I phi. And similarly, you can go ahead, you can say that okay, phi is equal to plus or minus 2 of phi 1 by square root of 2 pi e to the power of maybe plus or minus, I will write both together, I 2 phi, and so on, right. Now, you will realize that m is equal to plus or minus 1 or m equal to plus or minus 2. The solutions that we have written actually are complex, right. But if one is choosy, one wants a real solution, not a complex solution, that can be done, that can be arrived at, because after all the original differential equation says this, right. D square phi by d phi square is equal to minus m square, capital phi is what the equation tells you, and we have written a so complex solution by saying okay, e to the power of I m phi, but instead I could have said that the solution may be of the form cos m phi, right. You can see that this actually satisfies that equation, right. You just carry out two differentiations, you will find that this actually satisfies that equation. So, it is possible to say, instead of saying e to the power of I m phi, you could have said that a possible solution is cos m phi and another possible solution is sin m phi, correct. This is another possibility. The nice thing about this possibility is that there is no square root of minus 1 occurring in the solution. So, if you want, you can adopt such a solution, and then of course, it will have its own normalization factor. The normalization factor is not found to be the same as this one. You can actually carry out the process of normalization, and you will find that the normalization factor is square root of 1 by square root of pi in both the cases, not 1 by square root of 2 pi. So, therefore, if you want, I mean as far as this function is concerned, it does not really matter, right. I mean I do not have to worry, but as far as these are concerned, you see I can actually say okay, I will have a solution which I will write as phi is equal to, let me just write to the left, 1 by square root of pi cos simply phi is a solution, right. Here value of m is 1. So, I will have 1 as a subscript, but specifically the value of m is 1 and I have chosen a cosine function. So, I will put a subscript c and say that this is one possible solution, while what is the other possible solution, I will have phi 1 s. Why do I put s there? Because I am choosing the sign. So, phi 1 s phi, and that will be equal to 1 by square root of pi into sin phi. So, instead of choosing these two solutions equally well, I can choose these two also as my solution. The thing is, you see, many a times we want to be working with real functions, particularly these are going to lead to you to atomic orbitals, and atomic orbitals normally chemists are happier if the functions are real, okay, usually. Or instead of this, what will you do? Instead of these two functions, you can do exactly the same thing. What is going to happen is that you will have a function which will be cosine of 2 phi and another function which will contain sine of 2 phi. You can go do it for all the other solutions also. And in fact, we will be using these solutions when we discuss the atomic orbitals. That is the reason why I am telling you this. But there is of course nothing wrong if you want to say, okay, if you want to use these functions, they are also completely fine. So, now we have to look at the next equation, which is actually more complex. This is the equation that we have to worry about. So, we will look at that equation. Remember that theta is a variable that will range from 0 to pi. I have already told you that, and there is actually sin theta occurring here in this expression. So, what we will find convenient is to introduce a new variable. So, we are going to rewrite this equation in terms of a new variable, which I will denote as z. Now, this can be confusing because this is not your z coordinate. In fact, it would have been better for me to denote this by some other symbol. I mean, I can do that, but the reason why I thought I will use z is, you see, most of the notations that I am using are from the book, the famous classic book by Pauling and Wilson, Introduction to Quantum Mechanics. Introduction to Quantum Mechanics with applications in chemistry. So, that I mean, for using notations from that book is that if any one of you wants to look at the derivation, you should be able to use that book, and so it is better that I use the same notations as the book. But there is a minor difference that I have done. The minor difference is that, you see, that book is an old book and therefore everything is in CGS units, while here, because we have decided to throw away that system of units and use SI. So, I have modified things so that it is everything is in SI. So, I mean, actually I prefer to use, instead of Z, I would have been happier to use mu, but I hope there is no confusion and I can use Z. But if you wish, I can of course use mu and proceed. I have no difficulties, but it is better that I use Z. So, let us just say Z, but remember this is not the Z coordinate. So, if you have the Z coordinate, sorry, Z equal to cos theta, then naturally you will say, okay, what is dz? See, this equation I am going to express in terms of the new variable z, that is the aim. So, if z I define it to be cos theta, then dz will be minus sin theta d theta. and therefore, if you had something like d by d theta sin theta, suppose you had something like d by 1 by sin theta d by d theta, what is it actually? That is nothing but minus of d by dz, correct? See, dz is minus sin theta d theta. So, therefore, 1 by sin theta d by d theta, this whole thing is minus dz, correct. So, that is why it is minus d by dz, and now you will see the reason why this is convenient, because you have 1 by sin theta d theta here, right. But then you may say, well, there is a sin square sin theta here, what I am going to do is I will put a sin square here and introduce another sin theta here. So, that there also I have sin theta d theta, right. So, let us see what happens to this equation. Okay, this equation, the way it is written, it is going to become minus d by dz, right. I am just writing this operator. Then there is another sin theta d theta. So, therefore, I will have another minus d by dz, right, and that is going to operate upon theta, but theta, if I am going capital theta, but theta I am going to change the variable. Now, I have a new variable, and therefore, I will say, okay, this function capital theta of theta is actually equal to some new function p of z, right, because I mean the function will change when you change the variable. So, therefore, I will say, okay, p is going to be here, p is actually defined to be equal to capital theta of theta. So, I have written this part, I have written sin theta d theta, I should take care of sin square theta, but I know that sin square theta is 1 minus cos square theta. So, therefore, I can account for that by putting a 1 minus z square here, right. So, therefore, I have taken complete care of this part of the equation. Then what about the other part? The other part is going to be plus beta minus m square divided by sin square theta, that is very easy, that is nothing but 1 minus cos square theta. So, that is actually equal to 1 minus z square, and then I have capital theta here, but capital theta is my capital P. So, therefore, this is what happens to that equation, right. So, you can see that it is little bit simpler, not too much, but of course, I mean this negative sign and that negative sign are going to cancel. So, you can say this is what has happened to that equation. Okay, now you see this can be rewritten in a slightly simpler form by making a substitution. Well, this is going to take a little bit of time, so I will do it in the next lecture. What I now want to do is I want to say that this Pz, I am going to write it as 1 minus magnitude of m by 2, sorry 1 minus z square to the power of m by 2 into a function of gz, into an unknown function actually, and then I will ask what is the differential equation that g obeys. I mean the reason is not actually very obvious, but what happens is that if you made this substitution, then the equation that you get for g can be solved by the method that we discussed yesterday, by the series expansion procedure, where you will say that g may be written as a power series in in Z. Remember yesterday we discussed the harmonic oscillator, where we had the function h and this h was written as a power series in the variable x. In exactly the same fashion, if you make this substitution, you will get an equation for G, and that equation can be solved by assuming a power series expansion. And once you have a power series expansion, what is the result that you would expect? You would get a recursion relation, and you will want to terminate the series at finite power of Z, and you will have to impose a condition which ensures that the series terminates. So, we will see that in the afternoon. Thank you for listening.